Hello everyone, my name is Karan Gaikwad. Welcome to the week 4 project for advanced structural mechanics. The topic for this week's project is calculating the surface area integrals on the composite body and computing the flux of the scalar field. So the body that I've defined is a combination of a hemisphere and two cylinders, which is basically a table lamp. This is the parameterization for the hemisphere. I've defined two surfaces. One is the curved one and one is the circular one that is at elevation P. Coming to the surface one, that is the curved one, it is a function of phi and theta. I've calculated the area Jacobian by differentiating the parameterization with respect to phi and theta, which comes out to be r square sine phi, and then calculated the area by just integrating this area Jacobian with respect to the limits of phi and theta, which are 0 to pi by 2 and 0 to 2 pi, which comes out to be 32 pi. Similarly, for the surface 2, that is the circular area, which is a function of r and theta, I've calculated the area Jacobian by the similar cross product method above, which comes out to be r sine phi. And this I've incorporated into the area integral with the limits, with the respective limits, which comes out to be 16 pi here. Coming to the second part of my body, which is the cylinder, this is the parameterization that I've used for the cylinder. And coming to the area Jacobian for this, it comes out to be r, which is again the cross product of the differentials with respect to theta and z, which is the height. And then and then this area Jacobian is integrated with respect to its limits, that is h and 3h for z and 0 to 2 pi for theta, which then comes out to be 6 pi. Similarly, for the third surface, which is the base of the cylinder, which is the base of the lamp, sorry, for the cylinder. So this is the parameterization which is similar to the previous one. So this first line here represents the circular ring over here, which is at this connection point. The second represents the cylinder, and the third just represents the circular surface. So I've calculated the area Jacobian for all the four surfaces, for all the three surfaces for this part, that is R, and then integrated it with respect to its limits, which comes out to be 3 pi by 4. And then for the cylinder, the Jacobian comes out to be 2R, which then after the integration comes out to be 6 pi. And for the circle, Jacobian is R, which then comes out to be pi. And the total surface area that I've calculated by this manual method is 193.982. Coming to the normal vectors and defining a scalar field, I've used the scalar field from the past project, that is a function of x1 times x2 times x3. So it is basically a function of the coordinates. Coming to the surface one, which is the curved surface for the hemisphere, this is what the normal vector comes out to be. It is just 1 upon the area Jacobian into the cross product. And the normal vector for the surface 2, which is this circular surface, comes out to be negative E3. Similarly, I've calculated the normal vector for this cylinder as well, which comes out to be cos theta A1 plus sin theta A1 in the radial directions. Coming to the third part, the flux over the surface 4, which is this ring, is basically just E3. And for surface 5, which is the cylinder, it is similar to the cylinder in the previous part, which is, so the normal here is also similar. And for surface 6, it is just a cylinder with a negative E3. So this is how we calculate the flux, that is basically integrating with respect to the with the respective limits, and then it's a multiplication of the function and the normal vector. So this is how the scalar field turns out to be. It is blue, that is minus 60 when the function is in negative, and 60, that is yellow when the function is positive, and 0 at the center. So this is the MATLAB output that I've got, which is pretty close to the one that I've calculated by hand. The total flux here comes out to be this, which is pretty close to 0 as well, and the volume of the body is 148.175. That's it for my presentation. Have a good one. Thank you so much.